Okay, so let's get started with today's lecture. So I started last time mentioning essentially what the resource management problem is, and today we'll discuss it in more detail. For several reasons. First of all, it's important if you want to be able to mechanize proof search and linear logic. It's important to understand how to do resource management. If you want to implement anything related to linear logic, like even like linear type checking, things like that, resource management becomes interesting. It's also a good example for doing proof system engineering. How do we write a proof system so that we can prove the properties that we want? And how do we do the proofs about them? Okay, so there's some interesting questions and choices to be made when you think about how you want to prove properties of them. So it's a good example in various ways, in addition to being a very useful thing to be able to do. So I wanted to go through this in detail and see where we end up. Also, the last time that I thought about this, which was probably like 10 years ago or so, I've learned quite a bit since then, so I want to make sure that we kind of have a good sort of modern formulation of the thing. Okay, so the basic issue of resource management comes from the tensor to start with, okay? And so if you remember the rule for tensor, I'm going to omit gamma most of the time today because the unrestricted resources are very easy to manage because they're propagated everywhere, so there's nothing interesting going on. So just to save myself space writing, I'm just going to concentrate on the linear part. So the problem is this rule. Okay, if you're thinking about this rule bottom up, okay, you have to find a way to split the context and put some resources over here and some resources over there. And if you don't have the proof yet, you have no easy way at least, to know what should go there, okay? And so the idea is that you propagate all the resources to the left. And so what we do instead is we have delta proofs A tensor B. We propagate all the resources we have to the left, and we see which ones are used, and then we get some intermediate resources delta M, which have not been used, which are left over, and we'll pass these into the proof of the second judgment. Okay, and overall, if we have we need to generalize the conclusion as well. So if we have some input resources, then it will look like this. So all the input resources are given to the first sub-goal. We solve that some remaining intermediate resources are then given to the second sub-goal. Whatever that doesn't use, we output here. So that seemed a pretty simple idea, but now generalizing this to all of linear logic and everything linear logic has to do, and also be compatible with focusing, and take some effort and some care. So let's do that. Okay, so this is the first version of TensorR that we need, and there'll be a bunch more to come. Okay, so let's first think about implication. Okay, so the linear implication rule. Okay, so how would we do that in this new style? So we're trying to prove A implies B. Yeah?
It's very similar to a tensor, except that you move the B into the context.
You move the A into the context, you mean?
Oh, no, sorry.
Okay, tensor, implication left is very similar to that. I'm looking at the implication right rule. Okay? So how do we prove A implies B? Yeah? Okay, well, we don't know yet the output, but okay, let's delta I. Right? You always have to write this. Well, it's a good strategy to write these rules in the order that the modes dictate, right? Whatever you know, you propagate the things you know to the premises, you get the output. Okay, so at the moment we have an input, we're trying to prove that, right? So I'm leaving this blank on purpose. Okay. All right, so what does the premise look like? So we have delta I, and we add A to that, okay? And we try to prove B.
And then you have C delta O.
And then we get some output.
You have to make sure that the A is consumed in that part of it, though, right?
Right. So here's the tricky part, right? We need to make sure that this A which we added here is actually consumed because it's supposed to be linear, right? So this A must be gone, right? So how do we say that?
Delta O must be subset of
Okay. But there's still an issue that if there already happens to be an A in here, right? Need to be careful.
Delta I, comma delta prime, and delta prime is gonna be also output. I mean two.
Okay.
So we are gonna make sure that A is not in the delta O.
What was wrong with saying that delta O has to be a subset of delta I? Like in the multi-subset?
Okay. So you want to say delta O, let me write in the same order. Delta I gets reduced to delta O in the multi-set ordering. Okay, so it depends on how much you care about the specific proofs that you actually get, right? So if there's already some assumption A in here, you might want to distinguish those two occurrences of A, right? And so, for example, there might be a function that takes A tensor A into A tensor A. If you don't know anything about A, how many of these functions should there be? There should be two, right? One that takes this A to this one and one this to this, and one which switches those two around, right? So if you really want to be careful about the exact structure of proofs, you have to be careful about which A actually gets consumed as part of this, rather than doing just some of subset checking. Yeah?
We should write delta, comma, delta prime instead of delta I.
Here?
Yes. And so on the upside, we will add A, and output will be delta prime.
Okay, let me write it again over here. So we have delta prime A, B. Okay, and then, okay,
Delta prime in front upside, and on the bottom, delta prime.
okay. So what is the intent by adding delta prime everywhere? What does that help?
So we make sure A is not in delta prime. I mean output.
So you want to add another condition that A is not in delta prime?
No, C1.
Okay, so the idea is that because it's a new one, it can't be in delta prime because delta prime is down here to start with. So it has to be a new one.
So I think both rules are equivalent because if you can prove that the delta O is a subset of delta I, then there is delta prime and delta that fit in the future, right?
Yeah. So I think what we're struggling with here is that we don't really track the assumptions very carefully. So we can't distinguish really the two proofs here because we just put the things into the context, right? So there's a couple of ways to make this more precise. So one is you label each assumption with a new name that's different from all the names you already have, right? Okay. And so if you do that, then you could use this rule And you could say, okay, this is a new x colon a, right? The way we did it in the very beginning where we labeled our assumption with channels. And then instead of saying this, what would you say here?
X is not in delta O.
X is not in delta O, right? So we must have consumed this particular x because it's not left in delta O, okay? And there's implicit an assumption that when you add this, it doesn't occur already. It's added something new. So that's one way of doing it, okay? You just make sure that you keep names. And there's other reasons to do this. Because in the sequent calculus, if you want to give it a Corey-Howard interpretation, these are channels, so they're important to track the precise structure of the proof, okay? There's another way one could do it. So you could keep things in order, always, right? And then you could say something like, we add the x colon a on the right. And then over here, the right-hand side must be consumed, okay? And when you consume something, you don't actually completely remove it, but you put a placeholder that says this thing has been removed, okay? And so those two things, I think, are sort of equivalent. There's two different ways of doing this. So this is kind of convenient to do it this way if we just track, because in some sense we want to have a very precise representation of the proof anyway. So labeling our assumption is something we already did. Okay. Okay. So this is a slightly different way of writing the rules, but being sort of explicit about what remains. But I think that it's interderivable with this other version, so I'm just going to go with this one. Okay. Okay. Now, there's another problem with this, though. Okay. Okay, and the problem with this one, with the rule stated like this, is that we wait with checking this condition until we're done with this whole proof, okay, and then we check whether x has actually been consumed or not, okay. So what we should be doing instead of waiting at the very end and see has it been consumed or not, we want to fail as early as possible, okay. We want to know that it must be consumed, and we have to fail if it doesn't get consumed at the right places, instead of waiting all the way until we come back down here and say, oh, we forgot to consume this, okay. So instead of doing it this way, another way to do it is we have two sets of assumptions. One set of assumptions are the things that we must use, and the second one is the ones that we may use. Let's put it over here. Okay. So this time I'm going to write the gamma out. Okay, so these are the unrestricted assumptions as before. There's nothing special about them. These we must use. Okay, so there's no possibility of passing them on. They must be used in the proof. Okay, these here, they may be used. And these are the ones that remain of the ones that we actually may use. Okay, so we don't have a counterpart of the psi because all the things in psi must be used. Okay, so there's no possibility of passing on the residual ones that we haven't used. Okay, so if we use that, then what we can do here is we do it like oh, this was delta O, by the way. So we have some things that we must use, and we have something we may use, and we're trying to prove A implies B. And so what we do is we add x colon A here and prove B, and we just do it like this. Okay. So by putting it in here, it says in this proof we must use that assumption. So we don't just do some arbitrary proof and wait till the end and check have we used it, but we're trying to be aggressive about it so that as early as possible, when we know we must use it, it actually gets consumed. Okay, so now we have to revisit this rule, right? Because it's not that simple anymore. Okay, so let's see. Okay, we'll get rid of this. Okay, so we have a psi and a delta input, and we don't know the delta output yet, and we're trying to prove A tensor B. Okay, so now what is our more general form of these things? By the way, you hope eventually this kind of process will reach a fixed point in the sense that you have all the context you need and all the information you need. And sometimes it does after a reasonable amount of time, and sometimes it doesn't, and then you have to go back to the drawing board. So, but I did the work for this, okay? So hopefully I didn't make a mistake. So we're not going down a dead end. Okay, anyway, so how do we do this? We're trying to prove A tensor B. We have some assumption which we must use and some which we may use. Okay, so obviously the right-hand side is a given. Okay, now what assumptions do we have to prove A? No, hopefully not, because if we split it, then our whole program is ruined. Okay. We merge it with delta I. Okay. The point is that even if psi must be used in this proof, we don't necessarily have to use it over here. We could wait. So there's nothing actually that we must use in that, but we could use psi or delta I in that proof. Okay, but not, we don't need to use a psi here because it could be done over here. Okay, and out of this, we get back something that hasn't been used, call it psi prime or psi m, and something that hasn't been used out of delta, right? So these two pieces give us these two things that haven't been used. Now, what do we pass into B?
Psi m must be used.
Yeah, psi m, which we haven't used here, that must be used now in the second part because it must be used in the overall proof. So psi m goes here, okay? And what goes into the maybe used part? Delta m, right? And we get out delta O. And what do we return down here? Delta O. Okay? All right. Okay. So let's think about, okay, so we want to do this in the focusing calculus. Okay, so we want to make sure that whatever we do is compatible with focusing because this is for backward chaining search, right? So what do we do in focusing here? Oops, did I erase enough too much here? A. So we focus on A here, on A tensor B here. Okay, so that seems okay so far. So let's think about, let's say the one right rule. Okay, just to do something else. Okay, so we're focused on one on the right. Okay, how do we proceed? The things that must be used better be empty because we're at 1, so there cannot be any linear resources. Okay. And what about the things that we may use? We'll just pass those back. Okay. Okay. Oh, delta I. Sorry, of course. Okay. What about positive atoms?
Also must be used, can either be empty or can be fixed.
Okay. If it's a positive atom itself, then what happens?
Nothing else except so psi contains nothing else except.
Right. So this is the only thing in this context. And what about delta I? Can be anything. And we just pass it on. Okay. What if the P plus happens to be in the things we may use?
Then the psi must be empty.
Okay. So the psi could be empty, and we might have delta I with X colon P plus in there. And we're focused on P plus. And what do we return here? Delta I, right? Everything except for the one that we consumed as part of this rule. Okay, so this seems pretty good. We're making decent progress here.
We don't still need the name annotations, do we? Since we have the must context, just out of curiosity.
Well, okay, so here we need to move psi into here, and we need to be able to see here what came from psi and what came from delta. Right?
So couldn't we do that by an invariant and we still have that split? So when we're doing a...
You could do it by position. You could do it by position, right? So that would be one way to do it, or the other way to do it would be by labeling. Yeah. Okay. But since I like to have the names anyway for proof terms, okay, I'll just use the names. Okay. So now, what is the?
Can I ask a question?
Yep.
So what if we have to prove A times B, where A is a disjunction, which we can prove in both ways, like both of the subformulas of the disjunctions are provable when they use different resources, of course.
Well, A or B.
Yeah.
You just prove one of them. Okay.
But maybe the other one fails. Maybe the other one does not have enough resources.
Okay. Right. So that doesn't, to prove A or B, it's enough to prove A or B. Right. But if maybe proving A fails, okay, then you have to backtrack and now to prove B. And the two.
Maybe proving A succeeds.
Yeah.
But then when we prove,
Yeah. Maybe proving A succeeds using the wrong resources. And then later on you might have to backtrack and try B, okay, even though it succeeded in the first place, to maybe get a proof with different resources. Yeah. So that can definitely happen. Yeah. So the issue is, what about the focusing rule? When you focus on something, focusing on the right should be pretty easy, I think. Let's just see. How do I focus on the right? I have a psi, I have a delta input, and I'm trying to prove, something positive, right? Then I'm allowed to focus on the right. Okay, what's the rule look like? Well, as far as resources, nothing is going on, right? I just copy psi, delta input, gives me delta output, and I have to prove A plus in focus, and I return whatever that returns, right? There's nothing much going on. Now for left focus, is there anything interesting going on there? Okay.
We don't want to be focused on something that we don't necessarily have to use.
But we might have to use it, so we need it as a rule, right? Right? Okay, so there's I guess it parallels these things here in some sense, right? So it is possible that there's a formula which is negative in psi, and we have to focus on that. Where should we put the focus formula? Is this now something we have to use or we may use?
Once you focus on it, you have to use it.
Once we focus on it, we have to use it, right? So it has to be here. Right? Makes sense? If you put in delta I, we're just saying, oh, you focus on it, but don't use it. Okay, that seems wrong. Okay, it could be also a formula which we're free to use. Okay, and we have to make a decision that that's what we really want to do. We want to use it. So we could have delta I with, actually there should be a name here, x colon A. Oops, delta, I'm going too quick. Okay, so what happens in this case if I want to focus on this A? Yeah, we just have to move it to the left. We have to move it into here. And then I have delta I. Okay, and what do I return down here? just whatever's left over here, right? Because I've actually used this assumption. Okay? So it's good that we have this thing available, okay, because we also need to use the formula that we have focused on. Okay. Okay, let's look at the last one to look at is the implication. And then I'll try to formulate and prove that this thing actually is sound and complete. Okay. So the implication left rule, what does it look like? So the implication on the left, the formula is in focus. Okay. So where is it? In psi. So we have psi. And we're focused on A implies B. And we have some delta I. And we're trying to prove C. Okay? So what do we do in that case? We need to prove A in focus. Okay, and the psi has become optional together with the delta I, and we get out of this some kind of psi prime and a delta, or a psi m, did I call it? M and a delta m. Okay, and then what we do over here? Psi and B, psi m together with B, right? And then delta m. And that gives us delta O while we're trying to prove C. And here we return delta O. Okay? Okay, so this rule is actually problematic. This is not right, the way we wrote it. Anybody see what the problem is? Okay, so let me give you a hint. If we were doing forward chaining, this would be the right rule.
What is negative?
Hmm?
A is, if it is negative,
So
Yeah?
I guess we should switch over.
Right. Okay. So if we do forward chaining, and this is a forward chaining rule, then we match the premises of the rule, and then we generate the conclusion. So we match the premises. This comes first, and then we do that conclusion. Now, if we do a backward chaining, what we want to see is if this rule even applies, right? And for that, we need to look here first before we go back and try to prove A. So the example is from way back. If you have A arrow B, B arrow C proves C, with all these atomic formulas, right? And we're looking for a focus proof. Okay, and everything now, because we're doing backward chaining, is negative. Okay, which is the only thing we can focus on? Can we focus on this? No, because if we try to focus on that, it won't match the right-hand side. If we focus on this, this B minus will not match the C minus. We can only focus on this, right? This is the goal-directed nature of the search, that when we focus on something, we can only apply the left rule if this is a negative atom here that matches this negative atom on the right-hand side. Okay, so we want to focus on this. Okay, and if we do, okay, then the second sub-goal here is C minus in focus, proof C minus, but we haven't looked at that yet. And over here, from the remaining assumption, or actually from all assumptions, we want to prove B minus. Okay. So now we don't want to start the proof of B minus until we know that this C matches that one here. Okay. So the order here is wrong because we want to do this one first, but we can't because we get sigma m, or psi m, and we have delta m, which comes out of here. Okay. So what's happening here is that because our system becomes in somewhat low level, because we're talking about the specific steps of proof search, not about provability in general, suddenly we can distinguish between forward and backward chaining. Okay, and we have to have two different rules. So this rule has to change. So what we need to do is we put, what do we do? Do we put B here as the only thing that must be consumed? And then the rest of psi goes in here, is that it?
Yeah.
Okay, and we're trying to prove C. And if that succeeds, then we have to solve the subgoal. So we take the psi m together with, okay, and then delta m. And we try to prove A in focus. And we get the delta O out here. Okay, so the premises here are the same as the premises were before. Does it make sense now? Okay. So when you engineer these systems, you always have to be very careful, especially if you're making a strong commitment as to how we're going to use them. Right? This is we're trying to use these for a particular strategy of backward search, which works well with our system of modes and so on. And so we need to do this. We need to see if B matches the head first, and only if that succeeds, then we want to solve the subgoal. So that's how we have to write it. Okay. Okay. So. We didn't do width, but let me skip that for the moment, and let me try to make sure we can prove that this works. Okay. So these rules are obsolete. Okay, so you want to establish a relationship between the usual focusing calculus and this kind of resource focused calculus. Okay. So how do we do that? So if this was a homework assignment, prove that these rules are sound and complete, okay, with respect to the other ones. How would you go about this? Well, what's the other judgment we're trying to relate it to? The other judgment is gamma, semicolon, delta, proves A, right? So this is our usual focusing one, and this is the one with resources. And we want to show somehow a relationship between the two, right? So at the top level, what do we want, right? So the soundness of the system would say what? Well, or it should be, whichever one you want to do first, I don't care.
Gamma goes to radiating, the right goes to gamma on the left, and delta on the right goes to psi on the left. And we want to prove
So you're trying to say if this, then
then gamma semicolon delta those are
any objection to this?
I think yes, because some of them may end up being must use. Some of them could be consumed elsewhere. So I think you want to split up delta.
Wait. No. This is an ordinary linear logic thing. That means in linear logic, every assumption delta has to be used exactly once. So there's not allowed to be anything left over. So these have to end up, what we call delta here has to end up in psi. It must be used. Nothing is allowed to be left over. And gamma just gets carried over, right? So if I ignore gamma, which I generally do anyway, then we're just talking about this part. So delta has to be here. It must be consumed. There's nothing here. If there's nothing here, then there won't be anything here, right? Because these are only the leftovers, okay? So if this is, then this should be the case, okay? One might wonder if you could possibly prove that, right? But okay.
I suggest a more general form of this theorem.
Okay, well, we don't want to do that until we've tried to prove it and we've failed, right? Because if the proof works, right, then we're done. We don't have to worry about it. But yeah?
Oh, okay. I just feel that we will certainly fail at some certain.
Okay, we'll certainly fail. That's great. So tell me where we fail.
Because at the point you
Okay, so, I mean, this is a good way to do a proof, right? Find out where it fails. And the other way to do it is just do some cases and see if we fail or not, right? So, yep.
Well, when we invoke the induction hypothesis,
Yeah.
we're going to get something out where we have empties in the resources being passed over, which will match
Okay,
what we have.
yeah, excellent. So let's try. Which case would that be where that happens?
answer right.
Tensor right. Okay, so the case would be, okay, by the way, I didn't say this, but we should always notice it. Proof is by induction of the structure of this, at least proof attempt, right? Right. Okay, so the case would be that the proof looks like this, delta 1, delta 2, proves A, tensor B, because delta 1 proves A in focus, and delta 2 proves B in focus, and that's our tensor right roll. Okay, by induction hypothesis, we get delta 1 with nothing here, proves, actually I wrote it with the turnstile, forgive me for that, and focus. So that's by induction hypothesis. And by induction hypothesis, we also get delta 2 with nothing here, proves B. Okay? And that's also by induction hypothesis. What do we need to show at the bottom? We need to show that if we have delta 1 together with delta 2, nothing here, we get nothing here, we can prove A tensor B, right? That's what we need to show. Okay, how do we get from here to here? Well, we look at the rule we have for tensor right, okay, and trying to see if we can match that. So any chance of doing that? Well, how would you actually prove this in our new system? What rule would you apply? Well, obviously the tensor right rule. So in order to show that, what would it have to be? Empty, delta 1, delta 2. Okay. And then something. Well, something. Let's leave it open, right? We have some flexibility of deciding what that might be. And we have to prove A in focus. And I guess we have to name this so that we can talk about. But that's a variable here. When we want to apply the rule, we can figure out what delta M might be, because that's what we're trying to prove. And what would be the second premise? Delta M is a must use. And then two empties. Proves B in focus. Okay. Okay, now would anybody care to guess what delta M should be? We should choose it to be delta 2, right? Because this proof, we know, by this induction hypothesis, somehow should use delta 1 but not delta 2. Right? So we choose, and we have the right to do that, that it would be good enough if we could prove that. Now what about the second premise? That's the induction hypothesis. Excellent, right? We're in good shape. Over there, okay? Now the question is, can we go from here to here? Yeah?
Okay, well, now it's fine.
Okay. Well, the question is, can we go from here to here? Was it a yes or a no? As a no? Okay. Anybody bidding yes? Okay, maybe there's some lemma to do that. Okay. Okay, so let's think back the way we proved the completeness of focusing, right? We had to do an induction over the structure of proofs. And in each case, we proved some lemma on the other side, right? That this was actually an admissible rule. So the question is, if we know this, can we construct a proof of that? So two things happen here. First thing is, we move the delta 1 from here into here. If we have a proof where delta 1 is consumed, can we move it into here? Okay, so lemma, okay, if we have psi, and we have delta I and delta O, and we can prove A, then okay, I claim that this is true. Any objections? How do you prove that? By induction over the structure of, okay, a given proof here. And whenever psi is being used, okay, you can just move it into here essentially, right? Okay. Okay. So then, and then the second part is there's this delta 2 added here. So if we have, so if we move this over here, then we get a proof that says delta 1 is here, and this is empty, and we're trying to prove A. Okay, can we go from here to here?
Lemma again?
That's right. So what does the lemma say?
Well, we want to, if we have the proof, we want to be able to add in any extra context, which will just pass through.
Okay, then psi delta I, delta prime, delta O, delta prime proves A for any delta prime. Okay, should make sense. Okay, because what happens is you just add this new thing, and then you have to check all the rules, make sure that it's always passed through. And so the crucial cases is where it's supposed to be empty, like for the one rule. But when it's supposed to be empty, all we do is we pass it through, so we're allowed to do that. Okay. So yes, we can add something in. So therefore, so the step from here, so here's the first lemma, from here to here is the second lemma. Okay.
Could potentially simplify the other statement by instead of moving delta into psi, we can just move delta into delta I. Delta O, I think. That makes the structure of the proof simple.
Okay, potentially. I'm a little worried about.
We'd have like another lemma for the right side then.
Yeah.
Oh, okay. So
Yeah.
like, we're using the same rules.
So personally, I might just restate the theorem, the main
Yeah.
theorem, to allow arbitrary choice of the dot. I mean, instead of writing dot there,
Yeah.
I say that for any derivative in the original system and any choice of linear context, I can have delta prime outputting delta prime.
Right. So what you'll end up when you do that, actually, the proof gets a lot more complicated because you need to consider all the possible ways that this might be split into the two pieces. So, I mean, I think you can do what you said, okay, but as a proof organizational principle, if you can do it by induction of the structure of this and just use a couple of lemmas in each case, usually it's easier, it's more manageable, okay. So even though it doesn't look very general, it turns out that the thing you really need follows by a lemma. So you can do it. I'm sure you can do it the other way as well, but this is a good way to organize the proof, okay. All right. So if you believe all the other cases, okay, which is a big jump, but okay, this is, okay, that's my prerogative, okay. The question is now, how do we prove the opposite direction? Okay, so we need those two lemmas, but. Okay, opposite direction. So we have psi delta I delta O. Oh, I wrote turnstile for this. I'll fix that in the notes. Okay. Psi comma
delta I.
You have to take delta O out of delta I.
right. You have to take out the things you didn't use. Okay. Let me give a little bit of proof of A. Okay. So this actually seems easier. So let's check. Case would be this one here. All right. So what do we get by induction hypothesis on the first premise? So we get psi delta I minus sigma psi m comma delta m. Okay. Proves A, right? We throw them together with the comma and we just subtract out the thing that's left. Okay, what do we get by induction hypothesis in the second part? We get psi m together with delta m minus delta O. We get a proof of B in focus. Okay, so now we can apply the tensor R rule over here. Okay, so we have to put this together with that. So that's psi together with delta input minus psi m together with delta m together with psi m together with delta m minus delta O. Okay, what do we need there? We need psi with delta I minus delta O. Okay? That's what we need. This is what we have. Okay, let's see. Do we get exactly psi? So here we have psi. We subtract out psi m, and then we add it back in. So the psi part is accounted for exactly. Make sense? Now we need delta I minus delta O. So we have delta I. We subtract delta m. Then we throw delta m back in and subtract delta O. So it's exactly like taking anything delta I, subtracting delta O. Okay. So indeed, the two are equal. Yeah?
Is that assume that the output is always a subset of the input?
Yes.
Or we need to prove that?
Yeah. So I was cavalier about that. If psi semicolon delta I slash delta O proves A, then, so we could certainly prove delta I is a superset of delta O. Okay. Okay. We could prove something else if you wanted to. We could also prove that psi together with delta I minus delta O proves A with nothing left on the outside. Okay. I'm not sure if we need that, but it's also the case that psi together with delta I minus delta O with nothing left proves A. Right? So in some sense, this is almost like an internal formulation of the thing that we were trying to prove, right? Because now we say, these things are exactly the ones that are consumed, so we might as well move them over here into psi. Okay? Because they will be consumed. In this case, that will be empty, and we can move that. Okay. Okay, so modulo any mistakes, okay, on the connectors that aren't there. That should prove that our system is indeed sound and complete. So the resource management works. Okay. We should look at the rules for width, just to make sure that with the additives nothing funny is happening. By the way, this proof that we just sketched here, it's amazing how hard it is to come up with these kind of proofs. Okay, when you first design these kind of systems, right? Just to think about that. Oh, we want the lemma there. We want to weaken this thing. You know, there's a lot of head scratching in these things, right? It seems like it always works out when we try to do this here, right? Because I've already done it before. But if I came into the lecture and I had never done it before, right, we'd be sitting for an hour and 20 minutes trying to figure out what these things should be, right? So it's kind of, it's a weird thing about our field, by which I mean proof theory, which is what we're practicing right now. That, so the ultimate measure of success is that everything is trivial, okay? Because then you have done the right thing. The system is correct and the induction hypothesis is correct and everything follows very easily, right? And there's some hidden complexity there, which is not obvious, right? So here, the hidden complexity was mostly in the design of the system, to realize that you need a second thing that says, these are things that I must consume, these are things I can consume, and that's what's left over. Until we came up with that idea, the system was a lot more complicated than it would look here, and also the proofs were a lot more complicated than they look here, okay? Once you have that idea, then it's very clean. Okay, let's look at just width, just to make sure we didn't mess anything up. So if I'm trying to prove from psi and delta I, I'm trying to prove A with B. How do I do that? Okay, well, we write down what we know, and hopefully we write it in the correct space so that I can write in the rest. Okay. Okay, so what's the usual rule? You propagate all assumptions to both premises, right? So we have to pass everything here into the proof of A, and we don't know, it'll give us something back over here. Now, what's the second premise?
Exactly the same, and the two delta O's have to be equal.
Okay, so that's one way of doing it. So exactly the same. Delta I, we get out delta O prime, and we have a premise that says delta O must be equal to delta O prime, or we could just write delta O here. Okay, that's the way we're used to, like, skirting around that issue, right? If the rule applies, these two things need to be the same. Once you know the modes, what you realize you have to do is you pass in these things here, you get that one out. You pass in these things, you get that one out. Now, before you can return it here, you need to compare them. Okay? Now, this rule is problematic the way I've written it here. It's not the best we can do. What am I getting at? Okay. If I have A with B by modes, okay, which I first didn't write, we want to do A first, then B, right? We do this in order, just like for the tensor. We solve the goals in order, okay? So once I have this goal, I have a lot of information. I know what delta O is. In this rule, I'm ignoring that information, right? I run this thing as if I didn't know that, and I say, oh, do I get the right answer? If I get the same answer, yes. If I get the wrong answer, if they're not equal, then I backtrack, try something else. So how can I get this information I have from this goal into there? Well, okay. Everybody seeing it?
That I subtract delta O, you will be as equal. Delta in the end.
Okay. So we must use here delta I minus delta O. And there's no discretionary resources. We know exactly what we have to use, namely the things that were used over here. And also all the things inside. So then I don't have to check anything. I don't have to check this here. Why don't I have to check this? Well, because by this previous property, this is going to be empty, so I can ignore what's there. It's going to be empty for sure, because the output is always a subset of the input, so I don't have to check anything. Okay. Make sense? Okay. So we should see if we can also solve the top problem, right? So the top problem was we don't know which resources are being used. Okay? So how do we do that? Okay, let's write down the rule. Let's remind ourselves what the rule looks like. So we don't need this, so this is good. So even when you think, I think it's very important to think about these rules, each rule carefully, right? Make sure that it actually has the right shape. So I trust that you can write down the rule for bang, for example, and it will do the right thing. Okay, but the rule for top ordinarily would say this, okay, with any delta. Okay. So now if you have a psi and we have a delta I and we're trying to prove top, okay, how do we do that? So last time we said it's some subset, right? But we don't want to have to guess that subset. Okay. So how do we work around that?
We could just say this.
Okay, we could just say delta I. Okay, but then the rule for 1, is it still up there? Yeah, the rule for 1, okay, and the rule for top are almost the same except that the things in psi are consumed, right? And that seems questionable, right? So would the soundness or completeness proof fail here? Yeah?
But then, the ones that must be used.
Yeah?
Okay.
Well, the ones that must be used, these are okay, because we'll just use them. These may be used, okay, but if we're passing something on, we say this must be used at some point in the future. That's what we're saying when we're passing something on, okay? But actually that's wrong because it might not be used at some, it's okay for not to use it because it could have been consumed right here, okay? So as far as I can tell, you can only do two things. You can either guess, which is bad, or we can refine our judgment, okay? And what we should have is we should have two possible outputs for this judgment. One output is these are the things which definitely must be consumed. And there's another possible outcome, which is these things may be consumed later on. Okay. So if I have the judgment again, which unfortunately I erased, it's something like we have a gamma, we have a psi, we have a delta input, we have a delta output. And so that would be one possibility. And the other possibility would be that we have an input and an output which we are not forced to consume. We need some kind of a symbol for that. Okay. Okay, maybe that. No. Any suggestions?
C.
Okay. Now I want to call this delta because it's still a subset of that.
Okay.
I just want to mark it as some kind of... Okay. Okay. And so this means it must be consumed later on. And this means it may be consumed later. Well, so that, okay. So when you start out, you don't know if you need one or the other, maybe both at the same time. And then you play things through. And if I did make a mistake, okay, then I think you only need one or the other. Okay. But in order to be sure, of course, we have to replay the whole thing that we did up to now. Okay. And we have to generalize our proof of correctness, and we have to generalize, both directions and so on. Okay. So I don't want to do that. Okay. And the reason is because, well, first of all, this was worked out a long time ago. And secondly, in our In the language that we're actually going to use for implementation, which is CLF implementation, we don't have to deal with this issue because there is no top in the language. Okay. So what you need to know about resource management is already essentially on the board. Okay. But yes, you only need one or the other. Okay. And so if you look at the literature, you look at the papers, what you do instead is instead of writing in this two-way, you put a flag on this turnstile here, which is either 0 or 1. Okay. And now I can't even remember which one means which. Okay. You remember? Okay. So one of them means the assumptions that are here, they must be used. And the other one means they can be used. Okay. So Tara, do you remember which one is?
0 means we must use.
Okay, so 0 means must use and 1 means we may use it. And the intuition, I guess, behind that, the variable indicates if there's slack in the output, if you can remove things from the output. So 0 means there's no slack, 1 means there is slack. Okay. And then unfortunately, for each of these rules, like in this rule here, you have to consider 4 different possibilities, namely, this is either precise or it's slack, and this one is precise or slack, and then you get 4 possibilities here for the output. Okay. So it's a little bit tedious. Okay. All right. So fortunately, this is the fixed point, right? Once we have done that, all the rules are handled, all the resource managements are handled. You don't have to do any more generalizations. And if you're only interested in CLF, then we already reached the fixed point without this generalization, okay? Because all the things that happen in CLF are accounted for, okay? Now, jumping a little bit ahead here, but in CLF we have affine assumptions, okay? So affine assumptions are ones that you can use, but you don't have to, okay? So how would we accommodate them in this kind of a setting? Any ideas, suggestions?
You're already kind of using the delta I as like affine because you produce the delta O with those that you don't use.
Okay. So we might be able to hijack the delta I, right? Because it's something that you don't have to use. You can pass on what you don't use. So if we do that, then if we have a judgment that says we have affine assumptions. Oh, I'm running out of letters. Psi we haven't used yet today. Okay. We have linear assumptions. So these are affine. And these are linear. And we're trying to prove A. How would we call on this resource judgment? So what resource judgment would correspond to that? So the delta goes into the psi context, right? Because of the things we must use. The A stays over here. And what about the psi? And psi becomes the delta I, okay? And what happens with the output? Yeah? It's a subset of psi, so we ignore it, right? Because affine assumptions we don't have to use. Okay, so we just read them through. And if they don't happen to be used, we just ignore them. Okay. So now, of course, this is just a guess that that kind of thing would work. We would now have to go through our rules and make sure that it really does work this way. Okay. Any doubts? Okay, I don't see anything that would be wrong at the moment. But we do have to consider the new modality to make sure that we can actually model that. Okay, so let's look at the rules. So the rule for the at modality says that, okay, let's get rid of this. Okay, so if we are in delta and we have at A while we're trying to prove C, okay, then we add it to this affine context. Right, that would be the normal rule where we use it, where we move it from the linear context, it's supposed to be affine, okay, and then we move it into here, okay, where we don't have to use it anymore. So what would be the corresponding rule over here? So we have in delta, this delta is up here. We have in delta, we have at A, and we have a psi. Sorry, that's a delta I, which is our psi input, let's say. We're trying to prove C. So what do we do here? Well, we just follow that rule. Okay, and what do we do on the output side? Okay. What do we want to do there? Okay, two cases. This x colon A is still there. Okay, so what do we do if it's still there? Then we remove it. We didn't need it, right? So it would disappear like that. What if it reduced in this rule? It reduced in this proof, so it's no longer here. So if that was what do we do if it's no longer there?
Still just give back size here.
Yeah, we still give it back because we're allowed to use it, so it's okay, right? So either we remove it if it's there, if it's still there because we weren't forced to use it, okay, or we actually remove it, okay? So I think that the complexity of this system is the same as it was before if we have affine assumption. We can already accommodate them because the delta already behaves kind of like that, okay? In fact, there's a very close connection between affine and linear assumptions because there's very small to distinguish, very little to distinguish them. Essentially, only at the very end of the computation, where you check whether something, where you check if everything has been used, okay, or you allow some things to be left over, okay. All right. Okay, so that's resource management. Now, the sad thing is that the way we have done things so far, we have to have different systems for forward and backward chaining. And that's a little bit sad. Okay. And the reason is right here. Okay. The reason is that if you write it like this, then this would be a backward chaining because you need to look at this first. If this is a forward chaining rule, you need to match A first and then you generate B. So it has to go the other way around. Okay. And this is a general issue when you try to combine forward and backward chaining. The intuitions about the way the arrows behave, okay, is very complicated. Okay. So there is some convention that people follow. Okay. So when you have backward chaining, you usually write it when a backward arrow. So for example, if you say to increment n1, you get k0 if the increment of n gives you k. Okay, so you write the arrow, the linear implication, in the opposite way that we've been writing it all semester long. Okay. And the intuition is, because it's goal-directed search, right? We say this is our goal and we have to solve the sub-goal. So the backward arrow notation lets you focus on what you're trying to prove, and then you can see what are the sub-goals that you have to try to prove. For the forward chaining rules, we write them with a forward arrow, because we can look at the left-hand side, can see what it matches, and if these conditions are satisfied, we generate the right-hand side. So the forward chaining rules, they're naturally sort of read in the other direction. So we want to write them in the other direction to match this intuition, right? We said something like, if we have a return of, let's say, lambda x dot m of x to destination D, and we have a continuation that's waiting on D to apply the argument to a value to a term n. Then we evaluate, let's say, n for x in M with destination, D prime, with destination D prime. And we read it this way, right? If this condition is satisfied, then we generate this in the context. We don't say, if we want to evaluate n for x and m with destination D prime, then we find some kind of a return and some continuation. That's not how it works. Okay. So the convention is to write a forward arrow here and write a backward arrow here. So when we actually start programming CLF, which is going to be, I gave you a little preview, but we're going to start very soon. This is a convention I'd like you to follow. Okay. There's another thing which helps us there. So here, forward and backward chaining are the same rule in some sense, and we really get into trouble trying to do that. We actually distinguish at the logical level, not just at the level of the proof search procedure, between the forward and backward chaining judgments. Okay. And that'll be one of the next things that we'll tackle. So that in fact, there is two different rules, okay? But you don't have to look inside these things to see if you're forward or backward chaining. Okay, the rules, the judgments themselves of what you're trying to prove tells you whether you're inside forward or backward chaining. Okay. And there's multiple reasons for that, but one of them is basically is that you can distinguish so that at the level, at the logical level, between the two forms of inference. Okay, so you don't have to hedge your bets the way you do here, or write two different rules and get two completely different rules. Rule system for forward and backward chaining. Right? So if you really wanted to do it here, you'd have to have some separate condition basically saying that A implies B is a forward chaining rule or A implies B is a backward chaining rule, and then have two different rules, and you really don't want to do that. Okay. Okay, I think that'll be, so the two final pieces of the puzzles we'll have to put into place before we really have the full CLF is this, how forward and backward chaining are combined in a way that there is no conflict in rules like this, okay, so that they really work together well. And the second thing we need is to talk about unification. Okay, so a unification is necessary because when you have a rule like this, it has this n and k, which are really variables, and it should match any goal where you have variables in these positions. And last time we were writing these kind of equations when we were using the rules. We're saying k equals 0 k prime and so on. And this process is a process on the term structure. And that process is called unification. So to understand how the programming language executes, besides what happens at the logical level, we also need to understand what happens with these variables. Okay, so I will talk about that. And also the way to, how to resolve the forward-backward chaining kind of sort of overlap. We'll talk about that next time. I also brought out assignment 5. Okay, so you can go online and find it there. And I encourage you to pair up with someone and to do these things, do these together. But you don't have to if that's not what you would like to do. And there's, I think it's like 7 problems or something like this. You just pick one of them, and that's what you can do. And pick wisely. Okay. But they're somewhat open-ended in the sense that if it happens that the problem doesn't have an answer, okay, you just go as far as you can and say, okay, here I get stuck. Your problem was bad, incorrect, whatever. Okay. And maybe you don't get a publication out in that case, but at least you have something that you can hand in and get full credit for. Okay. So I've never tried this before, so we'll see how it goes. So be in touch if you have a question about how much do I have to do, or I'm stuck at this point, doesn't really make sense, I don't know how to proceed, just send me an email. Also, if you're interested in a project, and I know some of you are, because whatever this class is about is related to your research, for example, then by the same deadline, send me a research proposal for what you want the project to be. Okay. And then it'll be due at the end of the semester. And of course, if you do some kind of a project, it'll be bigger than each of these individual assignments. And I'll give you feedback on your proposal if you decide to go that path. Any questions on that? All right, I'm a little bit behind on the lecture notes, but I'll plan to catch up over the next couple of days. So, okay.